I have a double integral I want to do. Eventually, I hope it will become clear why I chose this one. I'm just going to compute it. Apparently, this region R, which has not been specified in any way yet, corresponds to these limits of integration, x from 0 to 3 and y from 0 to x. You may have figured that out already. Let's just compute the integral. First of all, leaving the outer integral alone and partially integrating x with respect to y, I get xy. As y goes from 0 up to x, and I still have the dx, which I haven't done yet. If I plug in the x for y, I get x squared. If I plug in the 0, I get nothing. So there's my new and improved and rather simple integral. And so now I'm going to get 1/3 x cubed from 0 to 3. Plug in the 3, I get 27/3. I get 9. That was easy. That was just a straightforward computation. Suppose now we take a look at these limits, because the outer limits here say that x goes from 0 to 3. And y, the inner limits, y is limited from 0 up to x. And this together, these two guys together specify r. Now mind you, the simple fact that there's an x in this limit of integration tells us this has to be y, because we have got to get this into the problem before we evaluate the x limits. Otherwise, we'd have variables left over in our double integral. Let's also take a look at these things. X equals 0, x equals 3, y equals 0, and y equals x. We know what these represent. If we sketch a quick little grid, x equals 0, well, x equals 0 is just the y-axis. And of course, x equals 3 is just a parallel vertical line. And if we go to y equals 0, well, we know what that is. That's the x-axis. And y equal x is our friend, the 45-degree line that we know so well. So let's see. Left, right, bottom, top. Pretty clear. That's R. It's that particular triangle. Okay? Let's do this all over again, but this time, let's start with the triangle. So I'll just draw it again. But I've decided I'm going to do something different, okay? We know that this is the point 3,3, right? We know that this is 0, this is 3, and up here at the top, it's 3 again, and this is R, okay? But this time, I've decided I want y to be on the outside, so y equals 0 to 3. Now here's y equals 0, okay, same as before, it's just the x-axis. And y equals 3 is just this horizontal line. Okay? So, I've got an infinite horizontal strip right now, all right? And I don't want to get this triangle, I want this triangle. So if I look at y equal x, the left-hand boundary, what's my left-hand boundary for x? It's got to be y. What's my right-hand boundary? Well, it's our old friend x equals 3. These are my new limits for R. Let's try it out. So this time, if I have the double integral over R of x with respect to area, I'm getting 0 to 3, y to 3, x. Now this time, this is dx dy, because y is my outer limit and x is my inner. Let's see how this integral works out. Well, let's see, 0 to 3, leave that alone. Integrate x, I get 1/2 x squared, as x goes from y to 3. So what's my new integrand? Put in the 3, I get 9/2. Put in the y, minus 1/2 y squared. And now it's time to integrate with respect to y. I'm doing the exact same integral, but with a different order of operations because I switched the x and the y. Integrate with respect to y, I get 9/2 y minus 1/6 y cubed from 0 to 3. If I plug in the 3, I get 27/2 minus 27/6. And it turns out that this is 27/2 minus cancel a 3. Okay, so I have 9/2. 9 from 27, 18/2. I get 9 again. Well, that's a relief. So it didn't matter the order in which I did it. We still got the same result. By the way, in terms of what's going on here, I'm going to add one more thing, a little bit of bonus information. If you integrate a function over a region with respect to area, and then you divide by the area of the region, this is what you call the average of f. My function was very simple. In both cases, I just integrated x. So, if we go back to our original right here, where we integrated this, the area of R, well, that's pretty easy, 1/2 base times height, okay? So, I guess it's 9/2. All right? So, my average, by the way, you know the name for the average of x, it's x bar. X bar is the centroid, or the center of gravity, or the center of mass. It's 9 divided by the area, we get 2. So x bar is around 2, and that's the balancing line that goes through the centroid of this object, this triangular plate. You'll see this in other forms later. We did x bar. We could have easily done y bar. One more thing for you. A more complicated problem. I decided to do y because my intent is not to have a fancy integral. I wanted a simple integral, and my region this time is a piece of parabola. X is going from 0 to 2. Y is going from 0 up to the parabola. And here is the integral worked out in detail. I get 16/5. If I instead look at this, notice what I'm doing. Now, y is going from 0 up to 4, and x is going from the left boundary, x equals square root y, to the right-hand boundary, the vertical line x equals 2. So, when I did the computation again, with the limits reversed, again, I got 16/5. You can decide for yourself which of the integrations is simpler, but they are equivalent, and it shows you when you're dealing with irregular regions, not simple rectangles where the limits are all constant, you do have a choice of how to describe the region. And that's the lesson for double integrals.